it's my great pleasure to welcome Nicola Gasparini, who to today's LCN lunchtime seminar. Nicola is currently an ICRF in the Department of Chemistry, where he joined us a bit more than 2 years ago, coming straight from KAUST. And previous to that, he did a PhD at the University of Erlangen with Christoph Brabeck, who I think quite a lot of us might know. And before that, he studied for a BSc and MSc in chemistry and organic chemistry and photochemistry and molecular materials at the University of Bologna in Italy. And Nicola is the newest recruit to the LCN, so it's very nice to have you officially joined today and to start off with a presentation. So
Fantastic.
Thank you very much. We look forward to hearing your talk today. Please, the audience, put questions in the chat or raise your hands, and we'll have time at the end. Thank you so much.
Thank you so much, Sandrine, for the nice introduction. Let me just share the screen and we kick off. I see on PowerPoint. Hopefully you see everything's clear.
Yep.
Laser pointer and getting to go. All right, thank you so much for having me here today. And as Sandrine said, it's the first time I'm joining the London Centre for Nanotechnology. I'm very excited to show some of my technology that I've done in the last years in the theme of nanotech. And in particular, today I'm going to talk about organic photovoltaics and photodetectors for near-infrared light conversion. You will see that one is quite a topic right now in the community, and we want to basically harvest as much light as we want in organics, photovoltaic, but also novel application on photodetector. I try to put some slides at the beginning just to keep everybody of us at the same pace. So what is organic solar cell? I think it's quite known now. It's quite a cool technology. It can be printed from solution with a roll-to-roll compatible method, quite light, and can also be used for building and integration. So it's quite interesting, like where the efficiency and this technology moved forward in the recent years. And in particular, I think every organic or any solar cell talk needs to start with this time to time very depressive NREL chart when we report or they report a deficiency per technology as a function of time. And despite we are still a little bit lower compared to inorganic technologies here, this full circle of organic, now they're experiencing very high efficiency, up to 18%. But when we go to model size, that is where I think we should start to look more into details and maybe moving from the so-called lab to fab production, where we want to generate more technology on module scale, where you see the gap going from 12 to 18% is quite big. But from where everything started is we need to date it back in 1985, where Professor Tang thought, okay, let's see if an OLED can also work as a solar cell, and indeed work with the efficiency of about 1 or 2%, as you can see here in these current voltage characteristics. However, in the so-called bilayer or two-layer organic photovoltaics, you can imagine that the photoactive region is quite low, and therefore a lot of charge recombination would occur. And the game changer was around 10 years later, when in the US and in UK, they developed the so-called bulk heterojunction, where the two materials, the donor and the acceptor material, was put together in solution and coated on top of transporting layer, sandwiched between glass, ITO, and silver as a top contact. And in this way, the interface between a donor and acceptor is throughout the whole bulk, and therefore we can now maximize the light to current conversion, and therefore not having problem by charge recombination. And there are a few processes. I think that one is important because throughout my talk I'm going to talk about a lot about photo generation, charge extraction. So in order to everybody of us to be on the same page here, at the beginning, the first process is the photo-generated exciton. It is formed either in the donor, in the acceptor, and together. And when the exciton reaches the interface, it can split in charge transfer state that eventually can be split in free charges. If that one occurs, and this charge can be transported through their respective electrode, we can have current generation, and therefore, hopefully, high efficiency. And there has been a lot of chemistry, physics, material science developing in the recent years. And I just want to put a little bit of attention in the chemistry at this point, just for the beginning, because a lot has been done by developing novel materials in order to achieve this high efficiency that I showed in the end-right chart. And in particular, P3HT has been the workhorse for this technology for many, many, many years. However, if you have you're just looking at the structure, the chemical structure, it is an homopolymer, so therefore quite limited by absorbing light. And there's been a lot of development with the so-called push-pull polymer, where combining a donor electron-rich and electron-poor material could allow to move or to extend the absorption towards the infrared part of the solar spectrum, as I'm going to talk today. And I kind of like this slide because it shows the development of these materials in terms of time and efficiency. And in the blue chart, we have the first generation polymers, as I talk here, where the efficiency was limited by around 6%. Then the push-pull polymer that I just discussed about took part, and the efficiency jumped over 12%. But the next step was to match the third generation of polymers with the so-called non-fullerene acceptor that I'm going to discuss in a second. And now with efficiency, as I said, experiencing 18%. So that was one side of the metal, the polymers. However, the big development has been done in the non-fullerene acceptor. We all know about fullerene, is a beautiful material. However, it presents a lot of limited absorption, normally absorbing only around 450 nanometer. So a lot of light has not been taken into account. And I was really lucky to be part of the development of this non-fullerene acceptor, in particular IDTBR, that has been developed here at Imperial by Professor Ian McCulloch. And very smart chemists, they took up what has been done for polymers and just deciding to basically using the so-called push-pull hybridization for non-fullerene acceptor, for small molecule acceptor. And in that way, you can imagine that you can modulate the HOMO-LUMO level, therefore changing their band gap, optimizing open circuit voltage and short circuit current density, and also those materials experience higher morphological stability and light stability. So really a good way to push this material further. And that was my introduction, and then I want to really go into my talk. And if you think it's already complicated what I discussed so far, what happened about adding a third component in so-called ternary organic solar cell, where I started to work in this topic since the day one of my PhD. And we're still talking about bulk heterojunction, but in this case, we consider three components. So the addition of a third component that, depending on their energetics, their chemicals, it can be seated at the donor or in the acceptor phase, but it can also be sitting at the donor-acceptor interfaces, co-crystallized with one donor or co-crystallized with the other acceptor. So you can imagine there is a lot of photophysics and physics and chemistry that can happen upon addition of the third component. But if we go step by step, and one can ask me why you want to make your life complicated. Now go back about 10, 12 years ago when fullerene was the acceptor using this technology. And with a donor depicted here in blue, while losing all this light coming from the solar spectrum in the infrared. And therefore, what about adding a third component with complementary absorption, which hopefully will lead to increased short circuit current density? As I said before, theoretically, like the open circuit voltage is proportional to the LUMO, to the difference between the LUMO of the acceptor and the home of the donor. Therefore, why not adding an acceptor in this case with shallower LUMO and therefore increasing open circuit voltage? And where I tried to give a contribution in this field was on field factor. In fact, field factor normally is modulated by charged combination processes. And I'm going to show you in the next couple of slides that by modulating charge-carry combination upon addition of a third component is also a way to increase the field factor of our devices. I'm going to do a little bit of historical background about that one, because otherwise it's going to look like that everything is working immediately, and actually it's not the case. Like always, took a little bit of time to understand Ternary and really finding design rules in order to optimize the efficiency of these devices. And in particular, back in 2015, first or second year of my PhD, I had this polymer PIDTQ in combination with fullerene, where the efficiency was not amazing, was still okay. However, I thought, okay, why not adding a third component like this silicon PCPDTBT, which has a complementary absorption, energy cascade alignment, so that one really should be a good material to work as a ternary solar cell. However, when I fabricate the devices, despite a very good light to current conversion in the infrared, as you can see here in the red curve upon addition of the third component, the power conversion efficiency was very limited, because in this way there was something going on, and the best way to check whatever is going on here is on morphology. And you can clearly see that from this transmission electron microscopy investigation, the binary present a very nice intermixed donor-acceptor phases, where in this case I can optimize a lot the charge dynamics. However, upon addition of third component, you see this cluster of fullerenes they are developing, and you can imagine that if I have a poor exciton sitting somewhere here, it will take a long distance in order to be separated, and therefore fill factor will be bad, because we're going to have a lot of combination coming from charge extraction in this case. Shall I give up? No, I didn't. And I thought about, okay, why not moving from a different polymer donor host, so the main amount of that. And I went from the previous polymer to PTB7, that back in the day is known to be a good material for OPV with efficiency about 7-8% in combination with PCBM, amorphous. So that one, I thought about it. Okay, let's see if I can improve the nanomorphology in this case. And it was a good idea, because upon addition of a third component in this case, I didn't experience the large fullerene agglomerates forming. And in particular, we were obtaining extremely high fill factor in these materials, with almost a record back in 2016 of 77%, which was almost about 10% higher than the binary devices. And it's quite important, like the amount of the third component you put inside is not always the same, depending really on your host system. 15% is what was the best in this case. And one way to look into what's going on in terms of charge dynamics is to look at the open circuit voltage as a function of light intensity, because this very easy measurement allows you to get inside into trap recombination. In particular, if you take your JV characteristics under different light level and looking into the slope of VOC versus light, you will get information of that. In particular, the closest slope to KT over Q, which is 25 millielectron volt, normally is a good symptom of trap-free system, whereas when it's higher than 1 towards 2, is for a system that is trap limited. And you see here that, again, the red one here with 15% of third component experiences the lowest KT over Q. Therefore, we envisage that in this case, not only we improve the nanomorphology, but also we reduce the traps of this system. And with further characterization that I'm not going to go into details, we really proved that our ternary with 15% of third component features almost pure bimolecular combination behavior, so no traps are in this system, reason of the very high fill factor in this material. And we wanted to prove that one, that is universal, so we moved from PTB7 to other two different polymers, and in all cases, the ternary had higher fill factor as a function of higher fill factor, not only at one sun over the binary, but actually over the entire light intensity spectrum, which is great because it really showed that you can modulate fill factor and therefore improving the efficiency of these materials. And let's go now move more towards our days. Like PM6Y6 is a blend that I think is very, very important to discuss about it. even in this framework, because that one was the game changer for our technology, because we were jumping from around 12-13% to over 15% efficiency just by combining these two great material developed by Professor Zhang Hu in China. And that was really, really great, because not only the efficiency was high, but actually every group in the world could achieve these record efficiencies. So that was great. And now that I discussed a little bit about ternary and looking into the absorption profile of these two materials is quite interesting, or I think now you can get it, what I'm going to do in the next slide. I thought about it, okay, why not adding a third component in order to really have a large light to current conversion throughout all the visible and infrared spectrum. And ITBR from Professor Ian McCullough was like the best candidate for it, because the energy alignment was really where I wanted to be, like in the middle between the donor and the acceptor, complementary absorption. So really, here the efficiency should go really high if morphology allows. And indeed it was. From 15% binary devices, upon addition of this magic 15% by third component, the efficiency was really improved by 16.6 with very high fill factor and no per circuit voltage. So one of the few cases where the addition of a third component allowed to improve all photovoltaic parameters in one go. That was very nice. And we were looking a lot at this material. In particular, we thought about it. The third component reduces traps. I didn't show here, but believe me. And can this effect have also an effect on photostability? And what we have done it here is by tracking the power conversion efficiency as a function of time under full sun illumination at open circuit voltage. So in a very, very drastic condition. And you can see here the ternary experience almost no losses compared to the binary, which is great. And has been known in the literature that trap-assisted recombination induces photodegradation. And the way that we thought in this story is the addition of third component reduces at time zero traps, and therefore under light stress, traps are not being formed, and therefore the photostability has been improved. We're having more studies right now ongoing to extend this light tracking over the course of over 1,000 hours, and we experienced something similar, but we are now trying to understand more in depth what's going on here. And I'm going to shift gears a little bit and going towards the new topic of photodetector. And I just put here these three bubbles because I think it's important that whatever we learn from OPV can be transferred to OPD, organic photodetectors. In particular, for this technology, we really want to have thick active layer because in that case, you can reduce dark current, which is a parameter that I'm going to talk in a bit. You want to have low charge recombination as well, and high throughput method because you want to, again, produce in large scale. And organic photodetector seems to be really the thing that takes into account all this information we know from OPV. And here I just put very briefly what I'm talking about, what is the key difference and similarities between the two tech. And we're still working in a diode architecture. Still our bulk heterojunction is the key player in photodetector. However, as I put here, we don't look anymore into the OPV operation of the current density voltage characteristics, but we look into the photodetector one, which is in reverse bias. Because in this way, we can optimize and extract all charges that we have from our devices. And again, it's important, dark current now is very clear, I think, because from the graph, because we want to optimize. It's similar to in a TFT, maybe you're more familiar. In that case, it's on off. In this case, light on, light off. And I had the privilege, and I was lucky to work at Siemens for a bit during my PhD, and the photodetector here was really big. And I just brought my best active layer, in that case, BTRHT IDTBR, also very good in terms of transport. I could process over 500 nanometers without losing, and we just made a photodetector on a proper TFT panel. So that one is not only a photodetector by per se, it's actually an imager. Those are real images coming out from my device upon light illumination from the bottom. in a 256 pixel matrix. And the characteristics were really great. Extremely low dark current in the value of -8 ampere per centimeter square. So that's very good. Highlight current, so could optimize my responsivity or external quantum efficiency, almost independent by the bias, which is again great because allows to have like materials that are pretty good in terms of charge destruction. And for technological relevance is also important, the so-called damping. So here is basically, without going into details, is how fast your device responds on light. And for video application, having a cutoff around 10K is enough. And in this case, we were able to go over 150 kilohertz. So we were quite happy that this material can be used for video application in principle. This one is just a nice slide to show, because at Siemens there were people jumping about that, in particular because just by putting an object, a very sharp object, we're able to see light on, object and no object in 1 pixel changes. Therefore, the MTF, which is the value for that one, was great, because in principle here, in a video, we could differentiate between two objectives from just 1 pixel from one pixel to the other. But again, you can tell me, okay, is that one really infrared? Can you do better? Yeah, I tried to do that one since I joined Imperial, and here with Helen, which just graduated from Oxford University from Professor Ian McCulloch's group, we're able to study the effect of novel polymers, in this case PTQ10, with these two non-Fourier receptors. And despite different absorption profile, we're able to get very good dark current for both devices in the power of -8, so similar to the one before. But for the case of FBR, here for the blend shown here in the visible, we're able to get extremely good photodetector in terms of performances, even exceeding the classic silicon photodiode that you're using, for example, to check your light intensity under the solar simulator or with a laser. So we were quite exciting. At the same time, a little bit sad that the IDTBR blend, the one absorbing more towards the infrared, was not working well. Not surprised, because we couldn't have a proper type 2 offset by HOMO. So most likely we're having a lot of recombination coming from whole extraction from these devices. Here, more characterization is quite nice, because especially the bottom one, I'm very excited to show that, because you look at here, we are looking really to picoamp current, so very, very low, with again very low light intensity. But and this value, for giving a little bit of we were discussing with my students about that, and this is basically a few photons in the room, in a dark room, and we're still able to catch them. Then we thought, okay, but can we then use what we learn from OPV and trying to optimize the blend with IDTBR? And that's what we've done with Tiani, my master student last year from the CPE, from plastic electronics. And we thought the idea. The idea was like, okay, we have problem about HOMO offset. What about we blend now IDTBR and FBR together with PTQ10 in the ternary blends to form ternary photodetector. There are a lot of people call it alloy. I'm not a big fan of this term. I'm just going to use it here just to keep everybody at the same page with literature. That one is the term that's been used. I have trouble thinking that organics can form alloy. However, despite that one, that's nomenclature. The ternary here in red had lower dark current compared to the other two binaries, which was great. But the most important thing that we observe is like the ternary in the visible had higher responsivity compared to the binary of IDTBR. So therefore, what I want to say is like I could use this method in order to improve the charge extraction in that case, and therefore having a specific detectivity, which is the value that allows to compare different technology, in the power of 12 joules, from 350 all the way to 750 nanometer, which is very good for application. Without going too much in details, what we believe is forming is IDTBR tends to phase separate and crystallize in the moiety of the acceptor, And we did observe that one from DSC, and therefore the thing we think is happening in this blend, we form a new crystal which had different energetics and therefore helping to split the exciton in the acceptor moiety and being extracted via Hall transfer from the polymer. My title was infrared detector, and I think you might have asked yourself during the last 10 minutes, oh, but you show us something that is 750, 800 nanometer. Can you prove, can you go further? And that's what we're doing with Paulina, my PhD student, together with Artem. And we are looking into this beautiful polymer TQT here with an absorption spectrum maximum at around 1500 nanometers, so really infrared, extending all the way to 2000. And you can imagine for this very narrow bandgap material, it's very difficult to find proper combination of materials and at the same time extracting those charges, so infrared. And what we're doing here is combining with the two non-Fulling acceptor Y6 and the IACO4F. And when we made devices, actually the device did work. Not surprising, the dark current is not as low as the one before. When you go very infrared, you have a lot of thermalization processes going on, which improve the dark current. Unfortunately, we are working on that. And at the same time, it's very difficult to find proper Hall and electron transporting layer, mainly Hall transporting layer, to have a ohmic contact and extracting holes. But despite this, we were very excited that we could get responsivity and specific detectivity all the way now to 1800 nanometer, which is one of the highest value for an organic photodetector so deep into the near infrared. So we're quite happy. We were doing further characterization, and in particular, it's important to check the LDR. LDR is basically you measure your device at different light intensity, and you want to have a linear dynamic range, because if you have, for example, for indoor application where you're not at one sun condition, of course, you want to have the linear regime of your short circuit current density or current density in order to extract at the same way charges. And a value of around 50 decibel is not too bad, it's not the record, but again, this one is all depending on the dark current. It's not very low, because imagine if you have dark current which is lower, then maybe we could get higher LDR. And again, very high damping, so for video application, that would be a good candidate. And Paulina studied a lot that one by transient absorption spectroscopy, and because we were wondering why, for example, we are having less responsivity in the case of the blend with Y6, and we observed that in the case of IACO4F, we have higher fast charge transfer, which allows to extract better the charges and therefore improving the responsivity. Again, morphology is very important even in this case, and clearly going from TQT IACO4F, we observe a more homogeneous blending of the donor-receptor interfaces, whereas in the case of Y6, we observe large aggregates, which also that one limits the charge extraction of these devices. And at the last part of my presentation, I just want to show you something that we were really happy to do in the lab and having a lot of fun. So in principle, if you have material absorbing in the infrared, you can direct getting your heartbeat, because the hemoglobin absorbs different way if it's oxygenated or not oxygenated. And then we thought, okay, if we connect directly the photodetector to a Keithley, which we can record current as a function of time, we shine infrared light on it, we put our finger between the photodetector and the light, we should observe our heartbeat with this very sophisticated homemade device setup. And indeed, it was working. And this one should be the other way around, but you can clearly see that just after a few jumping jacks in the lab, with my heart rate going extremely high by 130, just after a few minutes, after long years without going to gym, I was resting and therefore could get my heartbeat in the real time. So that one is an application I want to show you. I really believe that organic photodetector in the infrared can be the next thing for the technology. And of course, all this work cannot be done by amazing collaboration that I have at Imperial, in the UK, and throughout the entire globe. And with that one, Thank you very much for your invitation and attention, and I'm very happy to reply to any question you might have.
Amazing. Thank you so much, Nicola. This is, I think we've got a comment in the chat. This is so cool, indeed. And you really went through a lot of different concepts. So yeah, it's all very beautiful. So the floor is open for questions. Please raise your hand, type things in, unmute yourself. No, not so far. So, oh no, okay. I had a question sort of on I mean on the detectors. It's really it's really nice, and I need to get my head around this. But starting on the solar cell, when you were talking about your ternary blends, and you said that one worked really well, and I think it's from the ACS Energy letter. Because when you've got these three different materials, and you really need to have your energy alignments in the right way, and I'm trying to see this on a molecular level or nano level, because you need to have the right ones next to one another. Is this something that you can engineer, or maybe it's not that important, or?
No, Sandrine, it's a beautiful question. It's very difficult to engineer that because you're still starting from a solution where the three components are blended together, and then you deposit that on top of whole electron transporting layer. So it's I guess it's not as easy to engineer that, but we have from our side a very good tool, which is surface energy of the components. So we can predict if the third component is sitting either at the donor or in the receptor phase or at the interface. So we can have some ideas of what's going on. So yeah, we do have that one. It's not always the way to do. But for example, now before, and what I'm telling my group also, we never start blind to start ternary. We always try to find materials that are complementary in terms of absorption, energy alignment, and in the position that we think in the bulk.
Right. And then the surface energy. So do you need to modify your electrodes accordingly then to make sure that you've got no,
from the electrodes it's quite standard. We're still working with silver electrode on top and ITO at the bottom, and transparent conductive oxide. It's more really on the energetics and the material, the organic semiconductor material that we're using. On the electrode, I think what is very important right now is on the latter part of my presentation on the infrared detector, because with such a shallow HOMO for the really infrared one, all the whole transporting layer that are in the literature are not really good. Because I want to have aromatic contact, and basically I'm in this situation. So I'm having a lot of problem in extracting these charges. Therefore, dark current goes up, detectivity goes down.
Okay. Yeah, so you didn't really talk about the electrodes. So which ones are good candidates?
For whole transporting layer, we are still using PDOT, moly oxide.
I see.
So not a very sophisticated one.
Okay. Oh, it seems to work beautifully. Yeah. All right, great. Any further questions from? Not seeing anything. Okay, and those morphologies that you showed, were they based on? So those were TMs that you were doing?
That's right. Yeah, they were TMs. Like most of them, they were from Germany. In FAU, we had the Titan over there. So one of my colleagues was performing that. They were all bright field, I guess. And we had done a lot of elementary mapping as well.
Okay.
So we have a few papers on elementary mapping with the FTM. And energy LCN. And we have very good resolution. Actually, we recently published a paper when we develop a third component where it has like, that now I don't remember on top of my head which atom, but we track the atom and we're able to prove for the first time the position of the third component. Okay,
amazing. Right, yeah, so you can really start drawing these structures. Okay, that's awesome. So yeah, we've got a few EMs and getting set up also in materials, but it'd be really nice to have a look at that as well. And yeah,
absolutely.
okay. I don't see any further questions, so we'll leave it there for now, and hopefully continue these conversations when we've got our when we manage to get together again.
Exactly.
So yes. Thank you so much, Nicola, for this amazing talks on the materials chemistry devices. It really covers a lot. So thanks a lot for sharing this with us, and good luck.
Thank you so much for the invitation. Looking forward to see you again.
Thank you.
Bye bye. Have a good day. Bye bye.